Hey everyone, it's Adam again, and we're going to continue on with our talk of epi and biostats. This is going to be the second lecture, and we're going to be talking about continuous variables. So here are the objectives, and we'll cover these in detail as we move along during these slides. All right, first off, we're going to talk about the types of variables that you're likely to run into in the medical literature. So a couple of different types of variables we're going to run into. The first off being the independent variable, and then we'll also have the dependent variable. Basically, the independent variable is going to be what we call the experimental or the predictor variable, and this is basically what the experimenter, or if you were say doing a study, the variable that you can change, that you can manipulate to see what effect that it has on the outcomes. Basically, what you see is that the independent variable, because it is independent, because we're the ones that are setting it, will have a direct effect on the dependent variable. The dependent variable is going to be the outcome that occurs secondary to whatever you are changing with the independent variable. For example, if we were doing a study, we're trying to look at how good or how efficacious a new analgesic would be at different doses. The independent variable would be that dose of the medication that we would be setting, so whether it's 10, 20, 30 milligrams, and then the dependent variable that is going to be dependent on that independent variable or the dose of the medication with the change in pain scale. So for instance, if we did 10 milligrams of the drug, you would end up seeing, say, a pain score of 7. You increase the dose, say the pain score went down to 4. So that would be an example of both independent and dependent variables. And again, you can find that studies may have multiples of each. They might have multiple independent variables and they may have multiple dependent variables. It just depends on the type of study and what the investigators are looking at. Now, as far as the type of variables, getting into more details on those, we can have several types. I'm sure some of you are at least familiar with some of these to begin with. We talk about nominal variables, and again, these are going to be categories of things. So basically, it's kind of a categorical outcome with could be more than 2, but at least 2 outcomes that could occur there. So for instance, you're talking about blood types or eye color. The thing to note here is that there's no particular order of the different categories, and there's a difference in the magnitude between them. For instance, there's nothing saying that brown eyes are more or better than blue eyes. They're just different. There's no necessary order to them. Or blood typing, if you're A positive, B positive, or O, things like that. There's no particular order to them, no magnitude. Those are nominal variables. They're specifically just categories you're applying names to. Now, if you were to have, say, a nominal variable that was only had 2 outcomes, so say male and female, yes or no, that would be considered binomial or dichotomous. Basically, there's only 2 outcomes. Anything more than that would not be binomial at that point. So looking at ordinal variables, now these are actually going to be expressing some degree of order to them. There would be a rank and order of them, but they may not have an exact specification on the magnitude of difference between the different gradations thereof. So for instance, on a pain scale, if you ask 10 different patients, what's the difference between a 3 on a pain scale and a 4 on a pain scale, you may find there's a lot of differences in opinions there. Looking at level of education, whether high school, college, master, whatever happens to be. There's not particular an established magnitude of difference between those, but there's certainly an order, the hierarchical order to them. If you imagine going and reviewing a restaurant on Yelp or something, if you give it 1, 2, 3, 4, 5 stars, that would consider to be ordinal. So for instance, in this example of, poor, fair, good, and very good, if like on a Likert scale, you're doing, basically you'd say like, hey, we know that poor is worse than fair and fair is worse than good, but there may be some differences in between those magnitudes between poor to fair and then fair to good. Now, the thing you're going to probably see most often when dealing with the medical literature are going to be these continuous variables. Now, these are certainly going to have an order to them, and there's also going to be a very specific magnitude of difference between, say, one value to the next. So, for instance, we're looking at temperature, blood pressure, weight. 1 pound to 2 pounds is the same difference as 2 pounds is to 3 pounds. Okay, temperature, 98 degrees Fahrenheit versus 99, same differences between, say, 97 to 98. When you're looking at your continuous variables, you can break those down into further categorization. So for one, we have the interval variable, and basically this is could be a scale where it's a continuous scale. There could be equal intervals between say different values, but basically the 0 point is not considered to be meaningful here. So a good example of this is IQ. No one really has an IQ of 0, even though you might met some people who you think have an IQ of 0. But another kind of more concrete example would be something like temperature. So for instance, when you're looking at, say, Celsius as far as temperature goes, so again, here you have a difference, or the interval means the same thing all the way along the scale, no matter where you start at. For example, like I mentioned before, 99 degrees centigrade versus 100 degrees centigrade, the same difference is there between 100 to 101, okay? So that magnitude of difference between values stays the same regardless. For instance, with this, when you're dealing with these interval values, you can look to see, you can do differences between the two. So for instance, computing the difference between 90 degrees Celsius versus 80 degrees Celsius, that makes sense. But unfortunately, because the 0 doesn't really have a place here, because again, you can have a negative temperature. You can have a negative 30 degrees Celsius, because again, here when you're dealing with these interval variables, the 0 point isn't really meaningful, because here, if you're looking at something like 0 degrees centigrade, that doesn't mean no temperature. It just means that you're at say the freezing point of water, or whatever happens to be. And so again, if you're looking at this, you can't look at the ratio of these two values, because 100 degrees centigrade can't really be considered to be twice as hot as 50 degrees centigrade. So this is kind of the key point here of these interval variables, is that the 0 point is not considered meaningful. So the important thing to keep note of is that relationship with the interval variables, that you can do differences between them, different values, but you can't really do ratios necessarily. So for instance, when you're looking at these graphs plotting body temperature, say average body temperature of different animals, including humans, you're going to find that looking at these graphs are not super useful when you're comparing these interval values. So again, when you're looking at the relationships between, say, something like a dog and a platypus, you see here that you can't really take any difference here, because a lot of it depends on the scale that you're utilizing. And depending on how you set your scale, you can see that the differences here can be much more pronounced. So for instance, this same relationship holds when you're looking at on graph B here, but you notice here that the scales are much different. This is going from 0 to 50 degrees centigrade on this left graph on graph A, but here you're looking between 25 and 45. So even though the values are staying exactly the same between the two, you can see that the distances and the differences in the bars are much more pronounced. So again, here looking between a dog and a platypus, you can see here that it looks like a much greater difference. And so if you were to look at that, you might think there's a lot greater difference there than there actually is. So it's not really super useful, and these interval values can be very much influenced by the scale that you're looking at. Something like graph C might be a little bit better, because this doesn't really invite you to make comparisons on the ratios of the heights of the bars, things like that. You're just looking at different points to see how they compare the absolute values of one another. So on the flip side of the interval variables, we also have ratio variables. And here these are going to be categorized in these ordered groups. They have equivalent intervals between them. But here the 0 point is meaningful. So for instance, you can have 0 body weight. You can have temperature in Kelvin that goes down to 0, like absolute 0 is you cannot get any colder than that. So all energy is basically gone. You can have 0 mass, 0 distance. And so because of that, you can make meaningful ratios between the two. You can look at the ratios between values. You can do the difference between values. Whereas with the interval variables, you cannot really do this same thing with the ratios. So when looking at these various types of variables, there are certain things that are okay to compute with specific types of variables. There are some things that are not really going to be as useful. So for instance, if you're just looking at a frequency distribution, say for instance, you're just counting the number of things that pop up, say in your study. If you're looking at the number of males versus females, looking at the number of say people that rated your teacher's performance as poor versus fair, things like that. This is very easy to do, and you can do so with nominal, ordinal, interval, and ratio variables. That's no problem. On the other hand, if you're looking at something like median and percentiles, and we'll go into more detail on these in just a little bit, but I'm sure some of you are familiar with medians being just the middle value in a range of values. You can't really do that with a nominal necessarily, because the problem is there's no real difference between the different categories there. There's no inherent value difference between male and female, brown eyes versus blue eyes, so you can't really do a median necessarily because there would be no middle value there. On the other hand, you could do that with something like ordinal values because, again, there's an inherent order there. You can do this with interval and ratio values, no problem. Looking at adding and subtracting, this is only able to be done with our continuous variables, the interval and ratio variables, because of the fact that there is an established difference between the values and that stays the same. You cannot do that with ordinal values because, again, even though there is kind of a hierarchical order to them, there's no inherent specific difference between the two. So again, going from fair to poor, could be a much greater difference than going from good to fair, for instance. And then looking at things like ratios, we're going to see that's only really possible with our ratio values. You're going to see with the mean, and we'll also talk about things like standard deviation and standard error of the mean. That's only going to be possible with looking at things like our continuous variables, so things like interval and ratio variables. And then we're not really going to worry so much about this coefficient of variation, but that would only be done with our ratio values here. So again, this is just kind of a primer here. We're going to get more into detail on all these finer points as we move forward. So just kind of keep this table in the back of your mind and use this to review later on. Okay, so now we're going to look at how we can graph our continuous data to help us kind of make sense of it. So continuous data, you're going to see that this is going to be dealing with the results that are continuous in nature. So for instance, if you're looking at things like blood pressure, there's going to be an established difference between values that stays the same along the entire course. So that the difference between 10 millimeters of mercury of blood pressure to 20 is going to be the same as the difference would be from 90 to 100. You can do this with hemoglobin concentrations, oxygen saturation, temperature, anything like that. The first thing we want to do, though, is to be able to graph it so that we can visualize that data. Because, again, people are just not inherently good at looking at numbers and really extrapolating a whole lot of value out of that. And again, this is going to be much more common to utilize continuous data than you'll see in elsewhere in the medical literature. So this is probably the most common types, but depending on the type of literature you're looking at, you may see more use of things like nominal and ordinal variables. So the first thing you need to know are going to be the mean and the median of these values. So basically, we're going to use the set of data here that was done back in 1992 where they were measuring the body temperature for several hundred individuals. These are healthy individuals to see kind of what a normal temperature range really is. And so when we're looking at the data on the next slide, you're going to see what that looks like. And so the first thing we're going to look at is going to be the mean or the average. And again, we know this is going to be pretty easy to calculate. Basically, you're going to take all the values and you're going to divide by the number of observations, or we're also going to use the value n for that. So if we're looking at our sample size, or if we're looking at number of observations, n is going to be that number that we're going to look at. So n is a very important variable that we're going to be looking at and continue to look at as we move forward. So here's just a few data points that we pulled out of that data that I mentioned in the last slide. So here's 12 different points for 12 different individuals. And again, this is all temperature and centigrade. Basically, if you were to look at the mean of this, you would just add up all these values here from here, all the values together, and then divide by 12. And that should give you your average, which is 36.77. We'll talk a little bit about outliers later on, but outliers are basically going to be values that are going to be far outside of the ranges of what we consider to be normal just a little bit. So an outlier might on the upper end might be something like, say, 35 degrees centigrade. If someone was particularly cold, that would be considered to be an outlier. And we'll talk about those in much more detail later on. The big thing to note, though, is that means are going to be very sensitive to outliers. So for instance, if I did have someone who had a temperature of 35, I could drive down my average pretty significantly. Similarly, if I had someone who had, say, a temperature of 39, say they had a fever that day, that would be able to drive my average up. And so because means are very sensitive to outliers, it's important to establish and be able to recognize those outliers to see if they are truly different from the rest of the population or if there's something else going on there. So just keep this point in mind that means are sensitive to outliers. But based on this, we can see that the mean is one really good way to quantify the middle or this kind of central tendency of the data. This is not the only way, though, as we're going to see in just a second here. Now the median, as compared to the mean, is really just going to be the middle value that is occurring within the data. So because of this, it is essentially going to be, if you were to line up all 12 of those values that we saw on the last slide, and you were to line them up from smallest to largest, whatever that middle value is, or in this case, if you had, because it's 12, you would have an even number. You would just take the average of those two middle values. And so because we're simply ordering things, you're going to find that the median is not really going to be influenced by outliers very easily. So even if I did have a value that was say 35 or 39, you would find that it really doesn't shift my median very much. And so that can be another good thing to point out when we're looking at some of the other kind of features of the data as we're going to see as we move forward. But again, this is an important thing to keep in mind here, is that the median will not be influenced by outliers versus the mean that will be. Sometimes you can have what they call a trimmed mean, which is basically in order to remove the influence of outliers on the average, basically you could trim, say, a particular percentage off of the highest and lowest values, say like the upper and lower 10%. This will basically try to get rid of some of those outliers and remove that influence. So for instance, with Olympic diving, in order to make sure one judge doesn't throw the entire average, they will say trim off the highest and lowest scores. I'm sure any of you that are really into Olympic diving could tell me different, but that's just one example of it. In the medical literature, because we do not want to discount outliers, we like to keep those involved. We don't really throw out values like that. We like to include all of our values. So you won't see trimmed means being used very often in the medical literature. And one other thing you might see is the mode. This is the value that is done, or the value that is seen most commonly in a data set. Not very useful with our continuous variables, specifically because, again, these are usually going to be calculated to several decimal places, so most often you're not going to have a value that repeats more than once. Each one tends to be unique, but you will see that this can be this can be useful for variables that are only expressed as integers. So if they're only, say 1 or 2 or 3, not 3.96. Sometimes it can be more useful if you're looking at things like ordinal data or nominal data, where things are going to be in more like kind of categories or in their own kind of unique values. And again, this does not always assess the center of a distribution. You may find that the mode could be very well skewed towards the lower values, could be skewed towards the higher values. There's nothing that will tell you that, hey, this is in the middle. Whereas mean and median are going to be measures of central tendency. They're going to be kind of telling you where the values are lying kind of in the middle there. So some other lingos we're going to run into, there's going to be terms error and bias. So in the next figure, we're going to see that the temperatures range anywhere between, say, 35.7 to 38.2. Now, the reason you can have a lot of this variation here, not everyone's going to have the same exact temperature, can fall back on several different things. There's lots of biologic variability that can influence this. It could be things like age, their activity, diet, all sorts of things. And so what you're going to find is that anytime you're measuring values, especially from random sampling of, say, people or a population at all, you're going to find there's going to be some scatter there. It's just due to biological variation. It's not to say that anyone is particularly different than another. You could do the values the next day and find completely different results. Things like the average will probably stay about the same, but there's a lot of biological variation. There's some scatter there, and so it's important to be able to quantify this, and this is where we're going to talk about error and bias. So anyway, so we're looking back at that temperature data we were talking about before, where basically this is the entire set of data we have here, and here's that subset of 12 patients we were looking at previously. And so basically what you can see is that as far as the horizontal orientation, the points, they just scatter them in this regard, or in this way, just so that way they don't have overlapping of points. You can kind of see them all. But we call this a scatter plot, where basically all the points kind of get their own point on the chart. And so the important thing here is going to be this kind of vertical orientation. So you can kind of see where all the points are lying, kind of see where the central tendency is. And notice that not everyone has the same temperature. Everyone kind of scatters about quite a bit about the distribution here. And you note that the higher your value is of n, the higher observations you're looking at. So here it's like 130. You're going to find that you're more likely to have values that repeat. So you can kind of see here several values that all repeat around say the 37.8 area. sorry, 36.8, something like that. Versus when you have a smaller n, you're going to notice there's a lot more variability in the data here. There's very few points that actually overlap and actually have the same value. So because of that, we can see more scatter when you have a smaller n. So that's going to be an important point to remember for later on. But you'll see that with large data sets, this type of graph is not super useful because, again, we can't really derive a whole lot of information from this. You can kind of tell generally where the average is going to be, but that doesn't help you out a whole lot. So these kind of plots have kind of limited usefulness when you have many values or many observations. So again, some variation in the data could be due to, say, experimental error. Say you're measuring something imprecisely, that's a possibility. And so error, we're going to use this term, is often used to refer to that variability in the data. It doesn't mean that the information is wrong, it just means that there's going to be some degree of impreciseness or some degree of variability in the data. And so sometimes you can have biased measurements. These tend to result from things like systematic errors that are skewing your data one way or the other, depending on how the error is occurring. And you can find the bias can be caused by many factors that can consistently alter your results. So again, it's not just the preconceived notions of the experimenter may say, oh, I really want to show that this, this new technique for doing surgery really helps my patients. Some of it can just be due to the measurement bias that can happen there if you're not measuring things correctly. So rather than having that big scatter plot that we saw before, it was kind of difficult to discern kind of what was going on with a large set of observations. We have the same data here being represented. Both you can see here that N of 130 and then the N of 12. Instead of looking at it as individual points, these are what we call box and whisker plots. So instead of a scatter plot, box and whiskers. You can see the box here. You can see the whiskers kind of extending out from the boxes. And so, again, looking at both of these plots, they're showing basically the same information, but I'll kind of delineate kind of the differences here. And again, the medical literature, it's important to look at the graphs, but also look at their explanations of that, so you can make sure you understand specifically what the graph is telling you. So in this case, you're going to see that the horizontal line in the inside of the box is going to be that 50th percentile. This is the median. Basically, this means that 50% of the values should be higher than this point, and 50% should be lower than that. And then when you're looking at the outside edges of the box, in this case, you're actually looking at the 25th and 75th percentile. We call these the interquartile ranges. So the range between the 25th to the 75th percentile. Okay. Notice these do not have to be evenly distributed. It just depends on how the order of the values actually show up. So in this case, as you can see, that there are probably a lot more values on this end that end up having a little bit lower values and kind of driving your median down a little bit. So you kind of see a smaller distance between the 25th percentile to the 50th versus 50th to 75th. But regardless, just know that this does not have to be even. The median does not have to be directly in the middle of this box. And anyway, looking at the actual whiskers, in some cases you may find that the whiskers will show, say, the top 95th percentile values and the bottom 5 percentile values, and then you'd have kind of the upper and lower values being expressed here as individual plots or points. I've never seen this actually done in the medical literature. I've seen this type of graph much more commonly, where basically the error bars here, the whiskers, would show you the maximum value and then the minimum value. It's probably much more common here. And you'll notice that when you're dealing with a smaller number of values, so n is 12, notice how the box is much bigger than you see with the N of 130. Because of that, you're much more likely to see a lot more variability in the data, and so you have a lot bigger scatter here than you would see if you have a very large number of observations. So again, kind of keep that point in mind, because this will come back again. And again, when you have a larger number of observations, you're going to see less scatter in the data, you're going to see less variability here. So just keep that in mind. Another way we could do this would be with frequency distributions that actually let you see how many times a specific value comes up. And again, you can break these down in several different ways. Basically, what you can do is say put various numbers into a specific bin. So say anything that falls within that 36 degree Celsius would fall into one bin, 37 and 38. Notice this isn't super useful because you can't really tell much of the actual differences between, say 36.1 to 36.2 versus say 37.1. You can't really tell the differences there. You can start to put them into smaller bins. So you can see here it goes by half a degree Celsius each one, so you can get a little bit better idea of the scatter there, the differences. And this one would actually be looking at even smaller bins in this case. You'd actually be going via much smaller bins. You'd see a lot more of the actual distribution of the data here. Okay. And so sometimes you'll see this being referred to as a histogram being done. And again, the person who is presenting the data, usually the person running the experiment, has to decide, what the width of that bin is going to be, and that can be kind of a challenge because you want to show enough difference here. You want to be able to actually show some differences without getting the plot looking kind of too busy and not really easy for people to take a lot of information away from. So the next thing we want to look at is how we quantify the amount of scatter that occurs around the data that we're looking at. One of the most common ways that we use to interpret scatter around in a set of data is to look at the standard deviation. And basically, if you're looking at a mean value or an average value, that the degree of scatter around that average is going to be can be quantified by the standard deviation. Basically, it uses the same unit as the data, and we'll quantify that amount of scatter about it. And so we'll look at some graphs that show you specifically what that looks like. Again, very widely used in general, when you're looking at and evaluating a standard deviation, the larger that standard deviation or the larger that SD, that means the more spread out those values are, the more spread out the distribution is about that mean or the average value. So here's a graph kind of showing you kind of a standard bell curve and how values kind of lie within that, or kind of the distribution of values thereof. So essentially what you can see here is that for any given distribution, if you're looking especially at kind of the standard bell shape kind of curve, if you look at your average, it being this kind of value here, being 0, the general rule of thumb is that within -1 standard deviation to +1 standard deviation, so this range here, you're roughly going to get about 2/3 of the values. And again, I apologize for my handwriting. I'm normally left-handed, so this is all right-handed with a mouse. But anyway, so you can see roughly 2/3 of the population or the samples you're looking at should fall within these values here. Okay. If you want to take this one out even further, you can actually see if you were to look at 2 standard deviations, you see this is going to equate to about 95% of value should fall within this. 95%. So this will become important when we're talking about confidence intervals a little bit later on. But essentially, what we can see with this is that, say for instance, we're looking back at that temperature example. Say we were looking at the temperature for the N equaling 130. They saw that the mean temperature is basically 36.82. So you can see that 36.82 would be this 0 value here, basically be our average. And then if you were to look at 1 standard deviation above that, you basically would add 0.41 degrees centigrade, because you can see based on that calculation, the standard deviation is 0.41. You see that about 1/3 of the values would fall into this category here, being 1 standard deviation above. So roughly 1/3 of the values would kind of fall somewhere within the scatter here. And then another 1/3 of the values would be 1 standard deviation below the average, or say 36.82 minus 0.41. Okay, so roughly in this whole range between -1 standard deviation to +1 standard deviation, about 2/3 of the values here. And again, if I were to take another standard deviation below and above, roughly you get about 95% of the values being contained within that range. So in this case, if you were to look at this data again, all 130 observations, this isn't super useful to being able to look at and say, okay, well, I can kind of tell where the mean is. It doesn't really tell you kind of what that standard deviation is, the degree of scatter that we have here. And so this is a very nice way to represent this, where you basically have your mean value being dictated here, and then on either side you would have 1 standard deviation. So this basically tells me I know what the mean value is, and I can tell just how scattered out, roughly 2/3 of that data is going to be. And if you look at this, you can kind of see right here that if I were to extend, say this horizontally on either end, you can kind of eyeball and think probably that looks about 2/3 of the observations, about 1/3 on either end here above and below that. So it kind of makes sense if you're kind of looking at it from that perspective. Now, for the test, I'm not going to have you actually calculate standard deviation or averages or anything like that. It's more about the interpretation of these values, but it's important to kind of understand how standard deviation is calculated to understand the variables that go into that. So essentially, standard deviation is calculated by computers, but what they'll do is they'll start off with the mean or the average of the values that we observe, right? So for our example of looking at temperature, if we took those 130 values, added them all up, and then divided by 130, you get your average temperature, okay? What we're then going to do is that the computer will calculate the difference between each value and the mean. So every value that is below the mean, they'll take that and subtract it. Every value that's above the mean, they'll take that and subtract it. Once we get those differences, we're going to square each of those. We're going to add up all of those squared differences. And then what we'll actually do is take that sum and divide it by this n minus 1. Again, n is the number of observations we have, and this is minus 1. So this basically means this is called variance. So you're going to see that the number of observations we have is directly going to affect our standard deviation. Okay. And then once we take the square root of the value, you calculate it, and this is going to give you your standard deviation. So let me show you that in kind of the equation form. It makes probably a little bit more sense. Here's the actual equation that we use to measure or to calculate standard deviation. You can see here that x is going to stand for the value that we're using to subtract from our average. It's x bar. The bar at the top is going to be our average. You're going to calculate those differences for each value that you have. So again, this would be done 130 times in this case. You're going to square that value and then take the sum of them all. Okay. Once we do that, we can divide that by our n, which is the number of observations we have, minus 1. And then we're going to take the square root of that whole thing. Okay, so you can see how things like the number of observations you have is going to have a direct effect on your standard deviation. So the higher the number of observations you have, the bigger your sample population that you're looking at, you're going to find that's actually going to decrease that amount of variability in the data. You're going to decrease that scatter. Okay, so we'll talk much more about that in detail as we move forward. But again, if you're looking at your mean value here, to be right down the middle, straight as I can get it, again, about 2/3 of the values are going to be located within one standard deviation away from the mean, above and below. And then again, you're going to have 95% of values going to be within that range of 2 standard deviations away. If you were to go 3 standard deviations away, as you can see here, roughly you get about 99.7% of values. Again, you can see that even when you go out 3 standard deviations, there's still maybe a few outliers that you're not actually going to capture with that. In the medical literature, you're going to find that this 2 standard deviations value, this 95%, is going to be very, very important. This number is going to come up again and again, especially when we talk about 95% confidence intervals. This will be a very important number to keep in mind. The next thing we're going to talk about here is this Gaussian distribution, otherwise known as a normal distribution. Again, when we talk about normal here, this is not going to be in the sense that you usually speak about it. We'll see that normal is going to refer to a certain type of scatter of data. You're going to see what it means in just a few seconds here. So the origin of the Gaussian distribution, again, this is the traditional bell-shaped distribution that is the basis for most of statistics. Okay, this usually means that when you're looking at, say if I were to take a random sampling of, say 64 people, so like everyone in the classroom, you're going to find that some people are going to be below the average value, some people are going to be above the average value, but they tend to offset one another. That variability tends to offset in most cases, and so that most values tend to end up near the center. Most things tend to regress towards the mean. There's a reason why you hear that term regression to the mean, because most people tend to fall back towards that average. So as you get farther and farther away from the mean, you're going to see fewer and fewer values. That's why you saw that with one standard deviation away above and below that mean, you got about 2/3 of the values. Most of the people are going to fall within that one standard deviation away from the average. As you get farther and farther away, you're going to be getting fewer and fewer values being captured. And that's why you saw when you went from 2 standard deviations away from the average, containing about 95% of values, when you went up to 3 standard deviations, you only got maybe 99% of values. So there's a very small difference there because most people tend to regress back to that mean. Okay, so when you look at the data plotted, if you look on a frequency distribution, it tends to result in this kind of symmetrical bell-shaped curve. Okay, so this is called the idealized or the Gaussian distribution, otherwise known as a normal distribution. So I think most people are pretty familiar with the shape of a bell-shaped curve. You can kind of see this is kind of normal Gaussian distribution. What most statisticians do not want to show you is actually what the extended curve looks like. You can kind of see this nice shape kind of pop up over here. Usually you see a little extra detail going on. So anyway, but again, most of the time we're just going to be looking at this kind of the main body of this bell-shaped curve. So referring to the standard deviation, back to this Gaussian distribution, what we can see is that if you're looking at the ideal Gaussian distribution, which you can see in these curves here. The horizontal axis is typically going to be showing you kind of all the values that can pop up in the curve. The vertical axis quantifies kind of the relative frequency. So as you can see in a typical Gaussian distribution, that the majority of values tend to be right about the mean. That's why you have kind of the most values in it kind of being right here at the center. This is why the values tend to go up, and then as you get extremes of either end, you see the number of values in those cases kind of drop off. So this is a frequency distribution curve. So again, distribution tends to be symmetrical. And so in these cases, what you're going to actually find is that the mean and the median are going to be the same. And so this is actually one of the things that you can do when you're looking at data to determine if it is considered to be a Gaussian distribution or normal or not. Kind of a quick rule of thumb that you can use is that you can look at the mean and the median. If they are drastically different, chances are your data is not a normal distribution. If they are relatively close, you can probably assume that, yeah, this is probably normally distributed data. But anywho, that standard deviation is basically telling us it's a measure of the spread or the width of that distribution. So again, if you were to see some curves can look just like this, where you kind of have this particular shape. And so you can notice how these 2/3 of the value, kind of lie up to these points here, right? So 2/3 of the values here. You could have a curve that could start out, could be even wider. There could be more variability in the data. And you would see that those 2/3, so say I use a different color here, that 2/3 of the data, say, your standard deviation, say out here instead, there would just be more variability in this data is basically what that's telling you. So again, it all kind of goes back to the number of observations you're looking at, how variable the data is from the data set you're looking at, but just know that roughly any set of data that you're looking at, if it is considered to be a Gaussian distribution, 2/3 of the values will be within one standard deviation above and below the mean, and about 95% are going to be 2 standard deviations above and below. So you can kind of see the 95% here. And so when you're looking at these, again, it's important to understand that the area under the curve is going to represent that entire population or the entire set of data that you were looking at, the observations you're looking at there. So again, oftentimes you're going to find that a lot of medical papers are not going to necessarily show you every single data value that they actually measured. What they'll normally do is they'll tell you what the mean of the value is and they'll actually tell the standard deviation. That's generally all you need to kind of get a good sense of the data, to see how much variability there is in the data. Again, typically smaller standard deviations mean that the data is less variable. It's much more concentrated around that mean value, versus larger standard deviations tends to mean there's more spread in the data. It means that there's more values that kind of vary widely away from the mean value there. And again, if you assume the data is normally distributed, or if the authors of the study did test to show that the data is normally distributed, that's all you really need, because you can assume once you know what the mean is in the standard deviation, you can figure out the rest of the curve yourself, essentially. Again, we say normal and Gaussian distribution, these are kind of interchangeable terms, but one of the things we can actually do is if we were to set our mean value, so say we went back to that temperature example, we said it was 36.8 some odd degrees centigrade. If we were to say, okay, well, that's going to be our new zero value, it's kind of our new point of reference, this is our average value, and then we're looking at the standard deviation. If we were to say that this is going to equal 1, okay, basically you can call this kind of the standard normal curve. So basically that's what we were talking about before, where if you were to look at it, say you were to see here, if you have your normal curve, bell-shaped curve, this is probably not exactly normally distributed, but say this is 0. And if you consider one standard deviation away, you can consider 1. This value would be -1. This is considered a normal curve, essentially. And so what you can actually do is, if you were to say, well, how many of the values are going to fall within, say, a certain distance away from that average value? This is what we consider to be a z value. And so I'll show you a table of what that looks like in just a second. But basically, these z values are basically going to see, like, okay, well, if we're looking at a specific value, so in this case, say we're looking at so many of our standard deviations away, we'll take that minus our mean, which in this case would be 0. We can divide by our standard deviation. And so this will kind of tell us the fraction of a normal distribution that's between, say, -z and +z. Okay, so let me show you what that looks like in graph just for a second. So say, for instance, we were to look at a normal distribution. Again, I'm going to use my excellent drawing skills, just so we make sure we're staying on the same page here. So say we have 0, this is our average value. We're going to have 1, which is 1 standard deviation away, and we'll have -1, which would be minus 1 standard deviation away. So say, for instance, I were to say, well, let's see what percentage of values of the population that we're looking at here are going to fall into, say 1 standard deviation away. So if I set my value for z to be equal to 1, again, this would be 1 standard deviation away in this case. We're going to see that from -z to +z, we're getting about 2/3 of this value. So again, 68.27%. We mentioned, if you were to go, say, set our z value to 2, which again, in this case would be 2 standard deviations away, we can see that we get roughly 95.45% of this kind of 95% interval here that we're going to be seeing. So, and essentially you can set z to whatever you want. So in this case, you were to set z to, say, a little bit less than 1 standard deviation, say to 0.67, you would end up roughly getting about 50% of observations between -z and +z. Okay. So basically, this is something you may see in the literature every once in a while, probably more relegated to the statisticians, but just so you kind of have an idea of, you can kind of see what percentage of values fall within that range, and you can set that value yourself based on this kind of converting a Gaussian distribution over to this normal curve. So another important point here is that when we talk about things that are normal in the statistical sense, it does not necessarily mean normal in a clinical sense, right? It all depends on kind of what your observations are, the population that you're looking at, etc. And so again, we mentioned the Gaussian distributions are going to also be called normal distributions. I'll probably refer to it more as a normal distribution more often than not, but this does not refer to being normal in a clinical sense, but specifically in a statistical sense, okay? So for instance, it doesn't really make sense to define clinically normal limits symmetrically around the mean. Oftentimes we're going to give values, say for instance, we did that data on the whole population. We found that the temperature, normal temperature, or the average was, say, 36.89. Like, no one's going to remember that a normal temperature for a patient is 36.89. They'll probably say it's 37, right? So you may find that these values that we're looking at to consider to be our normals for patients may not be considered to be normally distributed typically. So just keep in mind there's a little bit of distinction there, but normal in the statistical sense refers to that distribution of values around an average. So another value that we're going to be looking at here is called the standard error of the mean. And so basically what this is telling us is if you were to look at, say, an average, say we were to take, say, say you have the whole U.S. population here. Let's say we have 1 pi, it's the whole U.S. population. And so we say, well, let's take a small subset, take a small sliver of that out. And so we're going to measure, say, let's do these 64 people in this class. We're going to say, let's measure all of you guys' average body temperature. So obviously, if you were to take the entire U.S. population and get that average temperature, say it may come out to something like, we'll say, 37.1. Let's say something like that, right? Now, if I were to measure just a small subset, which you may end up finding, it's something closer to, say, 36.8. Right. So obviously, if you were to take the averages, it's not going to be exactly the same, because again, there's going to be some variability there in the actual sample that we take that will not make it exactly true to the population average. So if you look at this mean value here for this small subset, you're going to find that the standard deviation tells you how much variability there is around that average. Okay. Now, if we wanted to figure out how close this average was that we measured out of this population and were to apply it back to see how close it was to the whole population average, we can do that using the standard error of the mean. And so basically what that is we will take the standard error of the mean is going to equal the standard deviation divided by the square root of the number of observations that we have, the square root of n. Okay. And so what it'll help us to do is that it doesn't necessarily directly quantify that scatter or that variability, but it tells you specifically how close that average is for that population you're looking at, and how close it is back to the actual population average. And again, you're never going to know the entire population average. You can't go out there and measure every single person out there, but you can see how close you are based on the sample size. And so the thing to note here, the larger the sample size, the larger your value of n is, the smaller that standard error of the mean is going to be, the closer you are to that average. So if my n was going to be 100, that's not anywhere near close to the U.S. population. But if I were to say changes to, say, 1 million, I would actually be a whole lot closer, because I would be able to kind of cancel out those high and low values and get closer to the actual average of what the entire population would be. So you can find is even if your standard deviation is large, depending on your sample size, you can find that the standard error of the mean can actually be pretty small in a lot of cases. So the larger the sample size, the smaller that value of SEM is going to be. Okay, so this means that you can get almost close to 0 with a very, very large sample size, meaning that you can have little doubt that the mean that you pulled is very close to that population. Okay, so again, we'll use this occasionally. It's probably not used as often as standard deviation is going to be, but it's another value you want to at least be familiar with when evaluating the literature. So again, not a measure of the spread of the data, but how well you can approximate your data back to the entire population. Okay? Standard error of the mean is always going to be smaller than standard deviation. So I mean, standard deviation is because it's divided by the square root of n. So because it's being divided by that, it's always going to be smaller. And so a small standard error of the mean suggests that the sample mean is very close to the population mean. Okay. So again, you may see this more in things like epidemiological data, where you're looking at a subset of people to see how closely they approximate the actual population, because you can never know what the actual whole population average is, but you can at least see how close your sample is going to be. And so this SEM, standard error of the mean, can be used to help us construct what we call confidence intervals around a sample mean. So we'll talk about confidence intervals in much more detail as we move forward. So now we're going to talk about the confidence interval of a mean. So basically what a confidence interval is us saying, well, how sure are we that the actual population value, so if I were to say, take this temperature example, say I was looking at that N of 130, there's 130 observations, and if I was to extrapolate that back to the entire population, say of the US, or say of people living in Florida, whatever my population I'm trying to extrapolate from is, I would say, well, how confident I am that the actual true average is to one of these values. And so you can calculate that using a confidence interval. And so basically, and we'll show you how to calculate this in a minute and what the components are. But if you're looking at, say, that value of 100, or a subset of 130 patients, and you can construct a 95% confidence interval, and you can say that I'm 95% sure that the actual population average temperature falls somewhere between 36.75 degrees centigrade and 36.89 degrees. Okay, so again, you're not 100% sure, and with statistics, it's never possibly 100% sure, but I'm pretty sure, 95% sure, that the actual true population value is going to fall within those ranges. Now, you can also calculate that for the 12 subset of patients. And you kind of notice here that the 95% confidence interval, because you have fewer people, you can't be quite as sure that they are representative of that entire sample, the entire population. So if you're looking at that, you can say, well, I'm 95% sure that the actual true population value is going to fall somewhere between 36.51 to 37.02. And as you notice here, that this range is going to be higher than it would be when you had the larger sample size. So that's going to be an important point we're going to come back to in just a second. Now, there's no uncertainty about the actual sample mean because we measure that ourselves. So whether it be the 12 patients or the 130, we measure that. So we know precisely what the sample mean is. But we can never really know with 100% certainty what that whole population average is because we don't have the whole population to actually measure. Okay. So again, this is why we are trying to get our best guess as to what that whole population average is. And we do that with our confidence intervals, right? Because the population mean is not known and can never be known. But what we can see is that by having these confidence intervals, which are going to be centered around the sample mean, we can get a pretty good idea of what it is with some amount of surety. So that confidence interval of a mean is going to be computed from 4 values. First off is going to be the sample mean. This is our best estimate of what the actual population mean is because this is what we actually measured. We took those 12 people or those 130 people and actually measured to see what we think. We know what the sample mean is, certainly, but this is our best estimate of what the population mean is. And so again, the confidence interval is always going to be centered around that sample mean. The next thing you need to know is what your standard deviation is. So again, standard deviation is a quantification of the variability or the scatter around the average value that we have from our sample. So for instance, if you were to look at, say, 2 data sets, you need to look to see, say, our average is going to be here, this line. And if you're actually looking at your standard deviation, what you would see is that the smaller the standard deviation is from the average, the less variability there is in that data versus something that, say, was widely scattered. There's a lot more variability here. Again, with one standard deviation away, plus and minus the average, you're going to find that this is roughly 2/3 of the values fall within either a very wide range, if you have a lot of scatter, or a very small range, very narrow range. What you find is that the confidence interval is proportional to the standard deviation. Okay, so the smaller the standard deviation, the tighter the data is, the smaller our confidence interval can be when we're actually figuring out, say, how likely we are to think that the actual value of our sample mean is going to extrapolate back to the population. Okay, so here I can say my 95% confidence interval is going to be a lot smaller than it would be with something that has a lot. So it'd be smaller here, we have a lot less variability in the data versus here we have a lot more variability. So larger confidence intervals needed to get that same level of confidence. We also need to look at our sample size. We mentioned that the larger our sample is, the closer we're getting to that population that we're interested in. And so the larger the sample size, the more likely it is to be close to the population mean. In a small sample, the sample is likely to be farther away because there's going to be more variability in that data. You have fewer people that can cancel each other out, very fewer values in either extreme to cancel one another out. So what this means is that the confidence interval is inversely proportional to the square root of the sample size, meaning that the larger your sample size, the smaller your confidence interval can be. Okay, and then you have to know your degree of confidence. So basically it's saying, well, how confident do you want to be in your value? So do I want to be 95% sure that my value falls in a certain range, or am I okay being 80% sure? Basically what you see here is that in order to be very sure about something, if you want to be 95% sure, you tend to need to widen out your interval. You basically need to say, like, here's a wider range of values that I can be fairly certain that the actual population mean falls within. Okay. So you can basically, I'm saying here, how confident am I that the true population mean falls within a given range of values? Okay, so all those four components are going to fall back into this and determine how big or small our confidence interval is going to be. So there are several assumptions you have to make when you are trying to determine the confidence interval of a mean. So again, some of the things you have to accept is one, that the sample that you're looking at, or the one you're evaluating in a piece of medical literature, is representative or completely random representative of that population. So for instance, if I were to try to measure, say, the average temperature, if I'm trying to take a sample and determine if it's, say, representative of the average population temperature, I can't take a bunch of people who, say, have hypothyroidism, because they're going to skew my data. They're going to skew on the lower end of things. If I was to measure every single person in the population, say, of the U.S., I would have people with hyperthyroidism and hypothyroidism to kind of cancel each other out. But it's really important that you see if the authors of the research at least attempted to get a representative sample to make sure that the people they're looking at are representative of the population you actually care about. So, oftentimes we talk about either convenient samples versus a truly random sample. So for instance, if you were looking at, say, rates of, HIV in a specific population, and you were working out of, say, a homeless clinic or something like that, or a clinic that, serves a higher homeless population, you would say, that's a convenient sample. It may be skewing your data one way versus another. And again, it all depends on what you define as your population. Okay, random truly means that, hey, you're pulling from a random sampling out of your population, and so there's usually some sort of mechanisms or some sort of, usually the authors will say how they attempted to get a truly random sample. In some cases, it may not always do that. So the other thing is you want to have independent observations, and so this basically means that every single person is independent from another. You don't want to repeat samples from one person to another. If you have siblings, they typically they violate this, or if people are measured twice, this can skew your data one way or the other. So in siblings, they have similar genetic conditions and may predispose them to, say, one value versus the other. So this is the reason why these people need to be completely independent from one another. We want to make sure that the data is accurate. So again, our CI is only going to be valid when the values that we are measuring are accurate. And then you need to assess the event that we actually care about. Okay, so 95% confidence interval is extrapolating from the sample back to a population for the event tabulated. But for instance, if we were to, say, measure people and we were looking at, say, we're trying to measure core body temperatures, but a certain piece of the sample that we had was measuring random oral temperatures, we know that wouldn't really be applicable, right? Because we know that oral temperatures run lower than something like a true core body temperature. So you need to make sure that the actual event you're concerned with is actually being measured here. And then the population should be distributed in a Gaussian manner. The most common ways we can do this is based on the assumption that we're coming from a Gaussian population. And there's some tests that you can do to test for normalcy, as we'll see a little bit later on. But again, this is the other assumption. You'll find that there's certain tests you can do for non-normally distributed data, but we'll look at that later on in the class. So if the assumptions are violated, basically this usually means that the confidence interval is going to be too optimistic, which means it's going to be too narrow, and that means that the true CI is likely wider than what you actually calculated out, right? So in order to be 95% confident of the value, it's typically going to be, you're going to find that it's your values are too narrow. You're likely missing what the actual true population average is. So again, with your calculating confidence intervals in the mean, you're going to find that computers do most of the calculations. Always note that the confidence interval is centered around that sample mean. It's always going to be kind of a symmetrical on either side of that, even though the variability you may find may go kind of well beyond that. But basically what you're going to find is that when we're calculating this, we need to know the standard deviation. We need to know what our n is, the number of values in that sample, and then also that degree of confidence that we want. And so what you end up finding is that you can determine the degree of confidence you have, and also based on the degrees of freedom you have, which you'll find degrees of freedom is actually equal to your n-1. You can get these t-tables, which I'll show you of just a second. T-tables will determine what you're going to multiply by your standard error of the mean, and this will give you your 95% confidence interval around that average. I'll show you an example of this in just a second, but just know that as you get with large sample sizes, you're going to find that basically your confidence interval for 95% confidence is going to extend 2 standard errors of the mean in either direction of the average. Okay, so looking at our t-tables here, you can see that based on the degrees of freedom that you have, so again, that's sample size minus 1. So again, if I was looking at a sample size of, say, 9, I would do 9 minus 1 to get my degrees of freedom of 8. And then I would figure out, based on how confident I want to be, and again, 95% is the most common, I would say, well, let me multiply my standard error of the mean by 2.3060, and then that would give me basically the range of my confidence interval. I would take this 2.3060 times my standard error of the mean, add that to my average, subtract it from my average, and you have your 95% confidence interval. As you get the larger and larger degrees of freedom, so again, larger and larger sample sizes, what you're going to find is that you get closer and closer, just a straight value of 2. So you can kind of notice here it's from about 1.9647 or so. So to really drive this home, let's go back to our body temperature example. So in this case, we're going to be working with that subset of 130 observations, so our n is 130, and they said that the average temperature is 36.82 with a standard deviation of 0.41. Okay, so if we were to take the square root of n, we get 11.4, and if you guys remember that the standard error of the mean is going to be our standard deviation divided by square root of n, so we take 0.41 divided by 11.4, and that gives us a value of 0.036, or standard error of the mean is equal to this 0.036. Okay, based on this relatively large sample size of 130, I'm going to go ahead and multiply 2 times the standard error of the mean, as we saw with that rule of thumb, and to get this value, 0.0719. So I know at this point that my 95% confidence interval is going to be 36.82, which is our average, plus or minus is 0.0719. And if you go back to that slide previously, you'll see that this is roughly equal to what they reported as their confidence interval. We see 36.75 to 36.89. What this means is that I can be 95% sure that the actual population value, if I were to take this sample of 130 people, and if I were to take this data and apply it back to the population that I was drawing them from, I can be 95% sure that the actual population average falls somewhere between 36.75 to 36.89. Okay. Notice that if I were to have changes in either my standard deviation, if the data was more variable, this would lead to changes in my confidence interval. Usually the higher the variability, the higher the standard deviation, the more variable, the wider this would have to be, the confidence interval would have to be in order to remain that 95% sure. And then my n affects this as well, so this is inversely proportional. So the fewer people that I had, so if my n was lower, you would end up seeing that the standard error of the mean would be larger I would end up having to multiply that by my, 2 times a larger number is going to make it for a wider range there. And so again, when the data is very, very tight, when you don't have a lot of variability and we have a large sample size, that means you have a very, very small, narrow confidence interval. And that means you can be relatively sure that the true values is within a very narrow range versus having a very large range. And so we'll talk about the clinical implications of that a little bit later. I just want to make sure you guys get the example here to note that what this confidence interval is really referring to in this case. So next up, we'll talk a little bit about error bars. And so error bars are basically this graphical representation of the variability of data. It's not that you've made an error, it's just telling us what the kind of the variability in the data itself is. And so the graphs help us to graph the uncertainty of a reported measurement. And so again, it tells us basically how accurate the measurement is. The smaller the error bars are, the more likely you are to have a very accurate measurement in these cases. And so in a lot of cases, you're going to find that these error bars represent one standard deviation of uncertainty, or basically one standard deviation above and below the average. Sometimes we'll do one standard error. Sometimes there are specific confidence intervals. So you have to really look at the table and look at the legends underneath it to see what specifically they're trying to look at here. So it needs to be explicitly stated, and I'll show you an example of that in just a second here. So here is an example. We're looking at a study in 2006 that measured how well the neurotransmitter norepinephrine relaxes the bladder. As you guys have covered in physiology, you know that norepi is going to be in the sympathetic nervous system, helps to relax the bladder to prevent urination. And so we're going to see that the data is related back to this percentage of maximal relaxation, or the percent Emax, that can be achieved in these rats. Very exciting information here, I know, but the main point here is to look at the data that we can see. So again, looking at the values here. So for instance, we're giving a concentration of norepinephrine to this rat bladder tissue to see what percentage of relaxation that we have there. And so you can see there's many ways we can report out this data. So one, if you can look at this table here, where you're actually looking at the mean and standard deviation. So you can see here the mean value would be this line here, with standard deviation going kind of positive and negative from that. This would be another chart which would show the mean value is this kind of horizontal bar having the standard error of the mean. Notice how this is always going to be smaller than the standard deviation because we're dividing by the square root of n. Okay. Here would be the 95% confidence interval. Notice here it's going to be larger than the standard error to mean, but it's typically smaller than standard deviation in a lot of cases. Median plus the range, so the range will just show you kind of the maximum and minimum values you can see here. And then in this case, you end up seeing the median plus the interquartiles. So usually when you're dealing with medians, you're going to, because that is basically the 50th percentile, you're also going to look at your quartiles. So this might be the 25th percentile versus 75th percentile. So just different ways of looking at all the same data. And again, if you were to look at these without having any idea of what they were referring to, it's hard to draw any kind of conclusions from the data. Again, just different ways we can plot the same information. So basically the mean plus the standard deviation on either end here. Sometimes you can have kind of a more of kind of the N bars on here. This is how you usually see it represented. B, C, and D, I don't see it done very frequently, but A is probably the most common one. All right, so we're going to do a little Q&A session here. Basically, ask the questions, kind of think to yourself. You need to pause the video to see if you have a good grasp on the concepts. Just kind of think through it, and we'll do the answers here in just a second. So, can the mean or the median equal 0? Can it be negative? Which is larger, the mean or the median? Are the mean and average synonyms? What units are the mean and median expressed in? Can the mean and the median be computed when n equals 1? How about when n equals 2? Can the mean and the median be calculated when some values are negative? And is the 50th percentile the same as the median? So for the first one, can the mean and the median equal 0? Can it be negative? Absolutely. The mean and the median can really have any value, including negative values and 0. Again, these are continuous variables. You're going to find that if you have negative variables included in there, they may skew the data towards 0 or towards negative values. Depending on the data, you may find that means or medians may be larger. Again, one of the things we can do to look to see if data is normally distributed is actually to kind of compare mean and median together. If they're very close together, that usually again means that the data is pretty normally distributed, but doesn't mean the one has to be larger or smaller than the other. Mean and average are synonyms, they're interchangeable. The mean and the median should be in the same units as the data it's expressed in. So whether it's millimeters of mercury, kilograms, whatever happens to be, they need to be in the same data there. Okay. Can the mean and the median be computed when n equals 1? Basically, if you have there's no point in looking at the data if you only have an n of 1, because again, you just had that one point of data. You need at least 2 for it to make any kind of sense. But certainly with 2 values, you're able to compute means and medians at that point. You just average the 2 values together. Can the mean and the median be calculated when some values are negative? Yes, but you're going to find that depending on the type of mean that you're looking at, some may only require positive values, but for our purposes, absolutely, the mean and the median can be calculated when some values are negative. And then is the 50th percentile the same as the median? Absolutely. All right, next up, can the standard deviation ever equal 0? Can it be negative? In what units do you express the standard deviation? Can the standard deviation be computed when n equals 1 or when n equals 2? Is the standard deviation the same as the standard error of the mean? Is the Gaussian distribution the same as a normal distribution? Are all bell-shaped distributions Gaussian? And will numerous sources of scatter always create Gaussian distribution? So the first one, can the SD ever equal 0? Can it be negative? You will find that the standard deviation will equal 0 if all the values are identical, because again, you're just measuring up all those differences between the mean to the value. You're squaring that. So in this case, you'll never find that the standard deviation will ever be negative, but you will find that if all the values are the same, then it would be 0, because again, the average would be the same as all the values there. The standard deviation should be expressed in the same units as the data, because again, you're not really canceling any of those units out at that point. And then standard deviation needs to at least have 2 values. Cannot do a standard deviation if there's only 1, because that's the only value you have there. And then we know that standard deviation is very, very different from standard error of the mean. SD is really only referring to the scatter of the data around the sample mean that we have, versus the SEM tries to tell us how close to the population average that our actual average is from the sample, comparing it back to the population there. Is the Gaussian distribution the same as a normal distribution? Yes, these are interchangeable terms. And then are all bell-shaped distributions Gaussian? You'll find that all Gaussian distributions are bell-shaped, but not all bell shapes are Gaussian. Again, you have to do those tests for normality to determine whether or not this holds true. Just because something looks Gaussian does not always mean that it is normally distributed. And then will numerous sources of scatter always create Gaussian distributions? If I know this is not the case, basically you're going to find that this is only formed when each source of the variability is independent and is additive with one another. So again, if you have something like matched values, or you have like siblings being measured, things like that, you're not always going to necessarily find Gaussian distributions there. So not always the case. Why do we look at a 95% confidence interval? Does the confidence interval of a mean quantify variability? Is the 95% confidence interval of the mean always symmetrical around the mean? Is the 99% confidence interval wider or more narrow than a 90% confidence interval? And what does the standard deviation quantify? And what does the standard error of the mean quantify? So again, the 95% confidence interval is pretty arbitrary for the most part. It's just whatever, for whatever reason, this is what the medical field has determined to be significant for us. And so that's what we're going to go with. So we generally look at the 95% confidence interval. Now, does the confidence interval of a mean quantify variability? No, it's not really looking at the spread of the values. Really depends on looking at the variability of the data, and it also is looking at the sample size. What we're seeing is that you don't expect 95% of the values to lie within that confidence interval of the mean. We're just confident that 95% of the time that you expect the population mean to be within that confidence interval, right? So I'm just saying that within these range of values, I'm 95% sure that this is the actual population average falls within these set of values here. Okay, and when we do journal clubs, we're going to find some examples of where we can apply this, and so that way you can get a better idea of what it actually means. Is the 95% confidence interval of the mean always symmetrical around the mean? It depends on how it's computed, but typically, yes, it is going to be symmetrical around the mean there. Now, how about a 99% confidence interval? It's going to be more wide or narrow than a 90%. The more confident you're going to be, in order to make sure you don't make a mistake, you have to widen out your variable, your range there. And so to be more sure, you have to widen that out widen out how the range of values there you can accept, and so it needs to be wider. If I'm going to be less sure about that, then I can use a much more narrow set of values there. What does the SD quantify? This quantifies scatter, how much of the values vary from one another, versus the standard error of the means quantifying how accurately we think we know what the true mean of the population is. Okay, and again, this is going to be quantified or determined back by standard deviation and also the sample size. Are the SD and the SEM expressed in the same units? Which is smaller, SD or SEM? If you increase the sample size, is the SD expected to get larger, get smaller, or stay about the same? If you increase the sample size, is the SEM expected to get larger, get smaller, or stay about the same? And then graphs often show an error bar extending one standard error of the mean in each direction. What does that denote? And then why are standard error of the mean bars used so often? So here we see that the SD and the SEM are expressed in the same units. So again, the same units as the data, whether it be blood pressure, heart rate, whatever it happens to be, which is smaller, the SD or SEM. SEM is always going to be smaller here because again, we're dividing it by the SD by the square root of n, so that's why SEM is smaller. If you increase sample size, is the SD expected to get larger, smaller, or stay about the same? You're typically going to see that SD does not change predictably, as is kind of quantifying the scatter around that average. While you do kind of factor in the sample size, it doesn't necessarily, it's not really as strongly affected by that. So again, it all depends on kind of the scatter is of the actual sample that you're looking at. If you increase sample size, the SEM expected to get larger, smaller, stay about the same. In this case, it would always get smaller. Okay. Graphs often show an error bar extending one SEM in either direction. What does this denote? And basically, this is the range defined by the mean plus or minus one standard error of the mean. Basically, the range of the confidence interval is going to vary with the sample size we're looking at. So, because again, SEM is going to be kind of directly proportional to how large our confidence intervals are going to be in those cases. Usually, two standard error of the mean either way, it's going to be based on 95% confidence interval. And then why are SEM error bars so often used? They're always smaller than SD, and in some actual ways, they're a more compact way to show just precisely how well you know the mean as compared to the population average. So that's why sometimes they'll use that a little bit more commonly. Okay, so that's our first recorded lecture here. So again, just a little over an hour. If you have any questions, please let me know. I'm certainly happy to discuss at any time. Thanks, and I'll see you soon.